In our last video, we talked about linear approximations and differentials using the tangent line to approximate the value of a function close to the point where we took the derivative. This was one application of the derivative. In this section, we consider a different application of the derivative, where we begin our exploration of the shape of graphs. We start in this section by exploring maximum and minimum y values and where they might occur. When we think about these things, we often refer to them as absolute extrema, where extrema is the plural of extremum, which is singular. Extrema and extremum can describe either a maximum or a minimum. Maxima and minima for plural. When we're talking about these, and we talk about an absolute maximum, we're talking about the highest possible y value on some interval, or perhaps on the entire domain of the function. We have to specify where we're looking when we talk about extrema. We use an interval of the independent variable, usually x, to represent where we're looking. Or we could again be looking on the entire domain. When we talk about absolute, there's no y value for the function that goes above that y value over that interval for the function. We can also talk about what's known as a relative extrema or a local extrema. Now, a relative or local extrema means that it is higher than the ones around or lower than the ones nearby, but not necessarily the highest or lowest over the entire interval that we're looking at. When we talk about these, absolute does not mean absolute value. It means highest possible y value or lowest possible y value in that region that we're looking. Relative means higher than the ones just to the left and the right, but perhaps not the highest, or lower than the ones just to the left and the right, but perhaps not the lowest in the region in which we're looking. When we think about Earth, we can think about the highest point on Earth, which is Mount Everest in Nepal, 29,035 feet. But the highest point in the United States is Mount McKinley in Alaska at 20,335 feet. If we think about these, Mount Everest is an absolute maximum on Earth. There is no place on Earth that is higher than the top of Mount Everest. Mount McKinley, however, is a relative maximum on Earth. It is certainly taller than the ones around it, but it is not the highest on Earth, so we call it a relative or local maximum. The lowest point on Earth is the Dead Sea shore, which splits in Israel and Jordan. It's negative 1,391 feet below sea level. The lowest point in the United States is Death Valley in California at negative 282 feet. Again, this makes the Dead Sea the absolute minimum on Earth, and Death Valley a relative or local minimum for the United States. On the other hand, if you were only looking at the United States and not looking anywhere else, we would say that Mount McKinley is the absolute maximum for the United States and Death Valley is the absolute minimum. It depends on where you're looking. If we include the Marianas Trench in the Pacific Ocean at negative 35,994 feet, this would definitely be the absolute minimum on Earth. It's more than a mile deeper than Everest is tall. Studying extrema lets us solve all kinds of problems, in particular optimization problems. These typically are looking for the best possible solution under a set number of conditions. For example, we might be looking to maximize profit if we're running a business, minimize the cost, minimize the materials used in producing some item to minimize the cost, or finding the maximum height of a rocket, the maximum velocity of a particle moving. In addition, we want to know where the extrema occurs. This is crucial in accurately drawing the graph of a function. We'll be exploring drawing the graph of a function more in section 4.5 and 4.6. Let me share my screen with you and we'll get started. So what are the learning objectives that we're going to be covering in this section? We're going to define absolute extrema, which we've already talked about in relation to highest and lowest point on Earth. And we're going to define relative or local extrema, which again, we talked about when we talked about the highest and lowest points in the United States. Then we're going to learn about what are called critical points of a function over some closed interval. We're going to talk about how to find these critical points and how the critical points can direct us to locations where extrema can, but don't have to occur. Lastly, we'll describe this in using these critical points to locate the absolute extrema over a closed interval. We'll be looking a great deal more at this in section 4.5. This section is a building block for accurately drawing the graph of a function using all the techniques and tools of algebra and calculus. Let's go ahead and define the absolute extrema more formally. Let f be a function defined over an interval I, and let c be some number in I. This symbol between the c and the I is epsilon and stands for let c be an element of the set I. In other words, c is in the interval I. We say f has an absolute maximum on I if f of c is greater than or equal to f of x for all other x in the interval. In other words, the y value at c is either equal to or above all the other y values. We say f has an absolute minimum on I, a low spot, if f of c is less than or equal to f of x, less than or equal to for all other x in I. We say that it has an absolute extremum on I at c if it has either an absolute maximum or an absolute minimum. Extremum is a more general term, and it could be either one. This is what's known as an existence theorem. It tells you that the extremum exists, but it doesn't tell you how to go about finding it. We'll need critical points and calculus to do that. It is possible, if the interval is not closed, meaning include the endpoints, or the function is not closed and bounded, meaning some of the y values go to infinity or negative infinity, that there are no absolute extrema in the interval. The basic graph, the cube or x cubed, is an example of this. If you think about the graph of x cubed, you know that there is no lowest point on the graph. It goes down forever. Likewise, there's no highest point because it goes up forever. This is because it's not a bounded function. Let's define more formally what we mean by closed and bounded. A closed interval includes the endpoints of the interval. And again, the interval is referring to the independent variable values, usually x or t. We use square brackets to indicate a closed interval. And you can see that here on the interval 2, 10. Open intervals, by contrast, do not include the endpoints. On these kind of intervals, we use round brackets. For example, it might look like this one, open to open 10. Now, you may be wondering about positive and negative infinity, where we always use round brackets. Technically, from a mathematics standpoint, they're considered both open and closed, but we always use round brackets. Now, what does it mean for a function to be bounded? A bounded function means that there's some finite real number for the y value that is either larger or smaller than all the y values over the interval. Now, this excludes going to positive or negative infinity, as we saw with the graph of x cubed. We say a function is bounded above if there exists a y value that the function never goes above. It may reach that y value, but it never goes above it. The minimum such value is called the least upper bound. It's the lowest number that the graph never goes above. We say a function is bounded below if there exists a y value that the function never goes below. It may go down to that value, but does not drop below it. In that case, we call that number the greatest lower bound. Let's think about the graph of sine and cosine. We know what sine and cosine look like. They basically, oscillate between -1 and 1. For both sine and cosine, the value of 1 is a least upper bound. It's the smallest number that sine and cosine never go above. They do hit the value of 1, but they never go above it. The value -1 is a greatest lower bound for the basic graphs of sine and cosine. They do hit -1, but they never go below it. It's the largest value. They never go below. There are other graphs, such as parabolas. Let's think about the graph of x squared plus 4. It opens up and it's been shifted up 4. It is bounded on one side, but not on both. When we talk about bounded, we're talking about y values. So there's an above and there's a below. This is clearly not bounded above, but it is bounded below. The minimum point on that parabola is going to be at the y coordinate of the vertex, in our case, 4. That means that the greatest lower bound is 4. It never goes below 4. It's not bounded above, but it is bounded below. Now, what about another type of parabola? What if it opens down? If it opens down, then it's bounded above, again by the y coordinate of the vertex, but it's not bounded below. A function may have both an absolute maximum and an absolute minimum, just one extremum, or no extremum. When we thought about the graph of x cubed, we saw that it had no absolute maximum and no absolute minimum. The graph of x squared plus 4 has an absolute minimum, but no absolute maximum. The graph of sine and cosine have both an absolute maximum and an absolute minimum. The absolute maximum y value is 1, that least upper bound. And the absolute minimum is -1, the greatest lower bound. It occurs infinitely often, but the absolute maximum itself is a single number, as is the absolute minimum. But again, it occurs infinitely often on the graph of sine and cosine. Let's take a look at some examples. Let's take a look at these examples. In the first example, we have the graph of x cubed, which, as we said before, has no absolute maximum and no absolute minimum. It also does not have a local maximum or local minimum. There's no point that's higher than the others nearby or lower than the others nearby. In the center graph, we have the rational function 1 divided by x squared plus 1. It has a domain of all real numbers. It does have an absolute maximum. Remember, the absolute maximum is the y value. Where it is, that's the x value. The absolute maximum is the y value, which is 1, and it occurs at x equals 0. It does not have an absolute minimum because the graph approaches the x-axis in both directions as an asymptote. It gets lower and lower, but it never gets there. But there is no lowest value that is graphed on the function. The last one we're looking at on the right here is the graph of f of x equal to cosine of x. It's also defined on all real numbers. It does have an absolute maximum of 1, which occurs at every 2 pi multiple of 2 pi. There's an absolute minimum of -1, which occurs at every 2 pi multiple of pi. Again, there's only one absolute maximum value. That's 1, but it occurs infinitely often. Absolute maximums and absolute minimums are single values that can occur many, many times. Let's take a look at the next set of examples. When we're looking at these examples, the one on the far left is a piecewise defined function. We have part of the graph of x squared plus 2 defined between x equals 0, closed, up to 2, open. It does not include 2, but it has a hole in the graph there. There's actually a jump at that point because the next section is defined over the closed interval from 2 to 4. It's the linear section, which is going to give us, I guess it would go through -3, has slope of 1. Now, when we're looking at this and we want to decide, does it have an absolute extremum? We need to find if there's a y value bigger than all the others, or at least equal to all the others. And there is. It has an absolute maximum of 2, which occurs one time at x equals 0. There is no absolute minimum, which often confuses students because it looks like, of course, that it's approaching the value of -2, and it is, but it never gets there. Absolute extrema are values that are on the graph, not the limit to the graph. And because it never gets there, that means that, well, -1.9, -1.99, -1.999, you can do that all day and never get to -2. There is no absolute minimum. When we look at the graph next to it, this is again the graph of x squared, which has been shifted to the right 2. So x minus 2, the quantity squared. When we're looking at it, it's only defined on the closed interval from 1 to 4. The one to its left was also defined on a closed interval from 0 to 4, but we had a jump in the graph. Notice that this one is defined between 1 and 4, and it's continuous. And notice that we do have an absolute maximum value of 4, which occurs at 4, and an absolute minimum value of 0, which occurs at x equal 2. The last graph is again a rational function, the graph of x divided by 2 minus x, defined on the interval closed 0 to open 2. We have a vertical asymptote when x equals 2, which means the graph is not defined there. In this case, we do have an absolute minimum value of 0 at x equals 0, but there's no absolute maximum. Looking at these, it appears that if the function is not bounded, then we may not have both absolute extrema. But that's not enough. If it is open, we may not have absolute extrema, as we saw when we were approaching this value on the left. So being closed and bounded, does that work? Not necessarily, because we may have a jump in the graph. We need to find the conditions under which we can guarantee that an absolute extremum does occur. That condition is continuity plus a closed and bounded interval. We need a closed and bounded interval plus continuity to guarantee the existence of absolute extrema. This is called the extreme value theorem, which makes sense. We could call it the extreme y-value theorem. If f is a continuous function, that means f of a exists, the limit as x approaches a of f of x exists, and they are equal, point to the same value. If f is a continuous function over the closed bounded interval from a to b, no going to positive or negative infinity, then there is a point in the closed interval at which f has an absolute maximum over that closed interval, and there is a point in the closed interval at which f has an absolute minimum over the interval. Notice that it includes the endpoints. Our absolute extrema could be at a or b or any value in between. The proof of this theorem is really kind of beyond us at this point. So you're just going to have to take it on faith. Keep in mind, if the interval is open, or it has even one point of discontinuity, it may not have an absolute maximum or an absolute minimum on that interval. Now let's define the relationship between local extrema, absolute extrema, and critical points. We've been talking about absolute extrema, but local extrema are higher or lower than the points nearby. We can think of this as the example of Mount McKinley or Death Valley in the United States, not the highest and lowest points on Earth, but the highest and lowest points in the United States. We want to take a look at another function. We want to see if we have absolute extrema or if we have relative extrema. Let's take a look at the graph now. Notice that this graph is continuous over its domain. It does have a pointy part or a corner up here. So I know the derivative doesn't exist there, but it is on the function. The function does exist there, and it is the absolute maximum of the function. Let's mark that down. This y value here, let's call it, what should we call it? M. M is the absolute maximum. Or absolute max for short. Do we have an absolute minimum? It depends on what you consider the function to be. We're told that this function is defined on negative infinity to infinity, which means that we have to assume that there are arrows here at the ends of the graph and that it continues to go down forever in both directions. That means that there is no absolute minimum. Problem is, negative infinity to positive infinity is not a bounded region. We did still have an absolute. Do we have a local maximum or minimum? We do. When we look at this one, we can see that we have both a point that is lower than the ones around it and a point that is higher than the ones around it. That means that this y value here, which I'm going to call j, is a relative or local maximum. And it's occurring at the value x equals 0. This value here has a y value, let's use n, and n is a local minimum. Just because it doesn't have an absolute minimum doesn't mean it can't have a local minimum or relative minimum. Let's formally define what a relative or local minimum is. A function f has a local minimum at c if there exists an open interval I around c on both sides of c, such that I is contained in the domain of f, and f of c is greater than or equal to f of x for all the x and I. Let's take a look back at our picture and see what we're talking about. On the picture, if we wanted to, we could take a small interval here that corresponds to these points on the graph. And in between that interval, that is the highest value that we have. It's greater than or equal to every other y value between the two red parentheses. We can do the same for the relative minimum. The definition of a relative or local minimum at C is if there's an open interval I containing C, have to be able to be on the left and the right, such that I is contained in the domain of f, function has to be defined there, and f of c is less than equal to f of x for all the x and I. We just say it has a local extremum if it's either a local max or a local min. Now, do we consider absolute extrema to be local extrema? The answer is it depends. If it's at an interior point of the interval, closed A to closed B, then yes, an absolute extrema is also considered a relative. So a relative extrema is a more general term in that sense. The problem, though, is if the absolute maximum or absolute minimum is at one of the endpoints, A or B. The definition of a relative maximum or minimum requires that you be on both sides. We don't know what happens on the left side of A or the right side of B. So if the absolute extrema occurs at one of the endpoints of the closed interval, then we do not call it a relative extrema. Let's now look at example 1, where we want to determine where the local and absolute maxima and minima occur. Assume that the graph is everything there is to see of the function. That means there are no arrows at the endpoint. Graph actually stops there. There are 4 graphs in this example. I'd like you to pause the video, label them, and then turn the video back on so we can discuss. Let's take a look at the first 2 examples. In the example on the left, there is an absolute maximum value of 60, and it occurs at about negative 3.6. I'm guessing. But I know the absolute max is 60. That's because I'm assuming that what's drawn is the entirety of the graph. It does not continue going. If it did, there would be no absolute maximum. I missed one I can see already, but let's go ahead and work our way from the left to the right. I do have an absolute minimum value of negative 40 at x equals negative 3. This absolute minimum value, because it's in the interior of the interval, would also count as a relative minimum. But this one would not count as a relative max because it's at the end point. The next one that I see here is at negative 1. There's a slight bump up in the graph. So I said that there was a local max of 10 at x equals negative 1. That was the best I could estimate. The next section that I'm concerned about is it looks, well, like it's flattening out around 1. I drew a question mark because I can't tell. It's too, well, small. The changes are too small to know for sure. Is there a point that is lower than all the others in that region? Maybe it's only 1/10,000th lower, so it won't show up to the naked eye. I can't tell, so I put a question mark. Again, there's a point here at 2 where I'm pretty sure that it goes below and it's a low point. But I can't tell exactly what the value of it is. I just know that at 2 does appear to have a local minimum. I do have another point right here, but this point, because it's on the end point of the interval, cannot count as a relative or local minimum. It's not the absolute because it's not the highest or the lowest. We'd simply leave it out. Looking at the next graph, this point on the far left at about negative 2.2 is the absolute maximum of about 10. Now, it does not count as a relative extrema because it's on the end point. Notice that we also have an absolute minimum on the far right at the other end point, which you see here, the absolute minimum of negative 20 at about 2.4. Neither of those absolute extrema will count as relative extrema because they're on the end points of the interval. The next point that I have is the one that I noticed that I missed. So let me fix that now. That's this one right here, which is a local min. And it appears to be at about, well, negative 12. And it's occurring at x equal negative 2. It's a local minimum because in an open interval about negative 2, it's lower than all the y values in that interval. Then I have a local max of 5 at x equal negative 1. Notice that at the value x equals 0, we appear to have a saddle point in the graph. Again, it appears to be a saddle point, but it is possible that there's a hidden extrema there. There's another local minimum of about 2.5 at x equal 1, and a local max of 7, roughly, at x equal 2. You can tell by looking at these graphs that doing it graphically, while it does get the obvious ones, is not so great in the gray areas. Let's look at the last two graphs. In the last two graphs, we do have an absolute max of 1 occurring at x equals 3. Again, it's an endpoint, so it doesn't count as a relative. We have an absolute min of negative 1 at x equals negative 3, which also doesn't count as a relative because it's on the endpoint. In between, we have 2 local minimums and 2 local maximums. We also appear to have a saddle point here at the origin. Again, it's very difficult to tell whether there might be a hidden slight bump up there and it's not truly a saddle point. When we look at the last one on the right, we have an absolute maximum value of 1, but it occurs twice, here at about negative 2.4, and again here at about positive 2.4. We have only one absolute maximum value, 1, but it occurs in 2 places. We have only one absolute minimum value, about negative 1.25, but again, it occurs in 2 places, at 2 and at negative 2. We clearly do have some local maximums of about 0.25 at negative 1 and at 1. There's a flat section in an open interval around x equals 0. But we can't tell from the graph whether there's a lowest point or a highest point, or if that truly is a horizontal section. it's horizontal, then it would count it as a, well, what would it count as? Well, it wouldn't. If it's truly horizontal, then you can't make an open interval on each side. Well, I guess you could. There it's lower or equal to all the others around it. So we would count that as a local minimum. As you can tell, looking at the graph is not a great place because of the scale of the graph. Sometimes an absolute maximum might be at 2,000. I don't want to graph that high. Sometimes the absolute max might be at 0.0001, which I'm going to miss with the naked eye. We need a better way of doing this. And that better way is through critical points. It turns out that extrema, these maxes and mins, either local or absolute, have to occur at what are called critical points, but not all critical points become extrema. Let's talk about what a critical point is, and we're going to talk about Fermat's theorem. We're going to let C be an interior point in the domain of F. That's actually a truly important statement, and what it's telling you is that the function exists at C. It's not a hole in the graph. It does exist. It can't be a vertical asymptote. The function exists there. We say that C is a critical point of the function F if either the derivative there is 0 or the derivative is undefined. That doesn't mean the function is undefined. It means the derivative is undefined. The function has to be defined there, or it can't possibly be a critical point. Remember that derivatives are undefined at corners, cusps, and points of vertical tangency. But the function is defined in all of those places. Just the derivative does not exist. These are critical points on the graph. Fermat's theorem, famous French mathematician Pierre Fermat, says if the function has a local extremum at C and it's differentiable, then it must be that the derivative at C is 0. In other words, what we're learning is that if we have an extremum, it has to be at a critical point where the derivative is either 0 or undefined, but the function is defined. Let's take a look at some graphs and interpret them in light of Fermat's theorem. In the graph on the left, it appears that we have like a downward opening parabola. There is a maximum, absolute max and local max because it's in the interior. And there is a point with a vertical or horizontal tangent line, which indicates that we do have the derivative equal to 0. This is a critical point. Let's take a look at the graph in the center. We have a cusp at C. The y value at C is clearly higher than all the others around, making it the absolute maximum on the interval and a relative maximum because it's on the interior. The derivative will not be defined at the cusp because there's no unique tangent line. We have the same issue when we look at the last one, which looks like an absolute value function with a sharp corner at C. The function is clearly lower at C than anywhere else on the interval, so it is both an absolute minimum and a relative or local minimum. But the derivative is not defined there because the derivative coming from the right has a positive slope and the derivative from the left has a negative slope. Therefore, the derivative being a limit does not exist. Let's look at these last two examples. In this example, we have a saddle point like we have in the graph of x cubed. The graph comes up, flattens out, and at one instant, it goes horizontal. And then the tangent line And then it continues to increase. There is no absolute maximum and there is no absolute minimum, but we do have a point right in the center of the saddle where the derivative is equal to 0. This is not a minima or maximum, but it is the location of a critical point. The last one on the right shows a graph, much like, well, none is coming to mind. The cube root of x. In the graph of cube root, there is a point where we have a vertical tangent line. That means that the derivative is not defined there because it has undefined slope. The function exists, but the derivative does not. And notice that while it is a critical point, this one did not turn out to be the location of an extremum value. We will learn more later on in section 4.5 about how to use critical points to predict whether the function is increasing, decreasing, and whether we have a relative maximum or relative minimum at a particular critical point, or neither. We'll do that through what's called the first derivative test and also the second derivative test. For now, we'll just have to use graphing to confirm whether or not we actually have an extremum value at the location of a critical point. What we want to do now is practice finding these critical points. Let's take a look at example 2. Find all the critical points for the function x cubed minus 12x squared minus 2x plus 1. In order to find the critical points, we want to look for 2 locations. 1, f prime equals 0, and 2, f prime does not exist. In both cases, however, the function must exist. So a good place to start is with the domain. The domain of this polynomial function is all reals, or negative infinity to infinity. In this case, then, we can simply go ahead and find the derivative of the function. F prime becomes 3x squared minus 24x minus 2. To find out where it's 0, set it equal to 0 and solve for the variable. When I do that, I'm going to have to use the quadratic formula because this one does not factor. In that case, I'm going to get x equals the opposite of b, which is 24, plus or minus the square root of b squared, negative 24 squared, which is 576, minus 4 times a, which is 3, times c, which is negative 2. All of this is divided by 2 times a, which is 3. Let's go ahead and simplify this now. 24 plus or minus the square root of 576 plus 24, all divided by 6, which turns out to be 24 divided by 6 plus or minus the square root of 600 divided by 6. 600 is 100 times 6, and the square root of 100 is 10. So this would give me 10 square roots of 6 divided by 6, which reduces finally to 4 plus or minus 5 square roots of 6 divided by 3. I have 2 critical points coming from the function equal to 0. 4 plus 5 square root of 6 over 3 and 4 minus 5 square root of 6 over 3. These represent the x locations, the where it is, but not the what it is. For that, I would have to plug it into the function. For now, We're not going to use the rules of first derivative test and second derivative test to determine what we have here. We're simply going to graph. Notice that the derivative is also a polynomial, which means that it is always defined. So over here, I would simply write none coming from that. Let's take a look at the graph of this now. When we look at the graph, you'll notice that we can't see everything. We know it's x cubed, so it's got to be having some part go up. And if I look at it, you can tell that, well, yeah, there is a low point, but I'm really having to scroll to find it. Down there somewhere close to negative 300. It's hard to see all the detail at the same time, but I do have a minimum and a local maximum, both. Notice that this one is occurring probably at the negative value, and the minimum is occurring at the positive value. Since we have local minima and maxima, we know they have to occur at the critical values, and I only got 2. So I know exactly where they occur. To find the y value, I would have to plug it into the original function, not the derivative. Let's now take a look at the next example, number 2, or 3. I want you to go ahead and pause the video and work out 3, 4, and 5 on your own, then turn the video back on and we'll discuss them. Let's start with example 3. It's another polynomial, 4x cubed minus 3x, so it's defined on all real numbers. Find the derivative, set it equal to 0, and solve. We get 2 critical points from that possibility, plus or minus 1/2. Because the derivative is also a polynomial, it is always defined. We have 2 critical points, but that does not guarantee that they're extrema. Let's look at the graph to see if they are. When you look at the graph, you can tell that in fact we do have both a local maximum at negative 1/2 and a local minimum at positive 1/2. Let's take a look now at the next example, number 4. This involves the natural log function, which has a restricted domain. Start by finding the domain of the function, because if it's not defined there, it can't possibly be a critical point. The argument to a natural log must be strictly positive, so we set the argument greater than 0 and solve to get a domain from 2 to infinity, open. When we take the derivative of natural log, we get the algebraic rational function 1 divided by x minus 2. This can never be equal to 0 because the numerator is 1. 1 is not 0, so we have no critical points from that possibility. When we look at the first derivative to see where it's not defined, we notice it's not defined at 2. That 2 is not in the domain of the function, so 2 cannot be a critical point. There's no critical point, which must mean that we have no relative or local or absolute maximum or minimum over the entire domain. Let's look at the graph to see if it confirms what we suspect. And again, when you look at this, there is no absolute maximum because it's going up forever, and no absolute minimum because as it approaches x equal 2 from the right, it goes to negative infinity. The last example I asked you to work was the function tangent of x. Tangent of x is sine divided by cosine, so when cosine is 0, it will be undefined. So our domain is all the reals except any pi multiple, pi over 2. When we look at the derivative of tangent, we get secant squared. When we think about secant squared, we can write it as 1 over cosine squared. But then we have the same problem we had last time. 1 is not 0, so there's no way that secant squared ever equals 0. There are no critical points from the first one. Where would secant squared be undefined? Again, when cosine is 0, but those are the very values we threw out of the domain. There are no critical points in this graph. When we look at the graph of tangent of x, we can see that there are no extrema. Let's now take a look at example 6. In example 6, we have rational exponents. Go ahead and pause the video to work out where you think the critical points are, and then we'll graph it and see if they correspond to extrema or not. For this example, it's helpful to rewrite the fractional exponents in their square root form. The 3/2 power is square root to the 3rd power, and the 5/2 power is the square root to the 5th power. This makes it clear that the domain includes 0 and goes to positive infinity, but excludes all negative numbers. I find the derivative by applying the power rule, and I also rewrote it in the square root notation as well. Notice that there is no value where the derivative is not defined that is in the domain. So we have no critical points coming from the second option. Setting the derivative equal to 0, I factor out the common factor of 3/2 x to the 1/2 power, leaving the factor 1 minus 5x, which gives me 2 critical points at 0 and 1/5, which are both in the domain of the function. Let's look at the graph to see if they correspond to extrema values. In the graph, it's not clear at first whether they are or they are not. We need to scroll in higher and higher until we can tell. At this level, we can see that we do, in fact, have a low spot at 0, and we have a high spot at 1/5. 1/5 becomes the absolute maximum, whatever that y value is, at x equal 1/5 becomes the absolute maximum. What would we call the point at 0? Well, it can't be a local because nothing happens on the other side. It's really nothing in terms of the graph, but it does help us graph it. Let's take a look now at the next example, which is number 7. Number 7 is going to involve either the quotient rule or the product rule if you rewrite the denominator with a -1 exponent. That will, of course, also invoke the chain rule. Go ahead and work this one now, and then turn the video back on and we'll compare our results. Let's look at the work now for example 7. I factored this rational function in order to find the domain, noting that I had to throw out -3 and 1. Then I found the derivative using the quotient rule. You may have preferred to use the product rule and the chain rule. It shouldn't matter. You should come up with the same value for the derivative, 2 divided by the quantity, x plus 3 squared. The first derivative is never equal to 0 because the numerator cannot equal 0. 2 is never 0. The first derivative also does not exist at any point that's in the domain. So, or rather, there is no point in the domain where the first derivative does not exist. The only point in question is -3, but it's not in the domain. That means that we have no critical points which must mean that we have no relative extrema on this graph. Let's look at the graph and see what it looks like. In this case, we see the typical rational function. There is no minimum value because the graph goes down forever as it's approaching -3 from the right. There's no maximum because as it approaches -3 from the left, it goes up forever. There is also no local min or max in the interior of the region. Let's now turn our attention to the next one, which is deceptively difficult or deceptively simple. It looks simple. It may not be as simple as you think. Let's take a look at the critical points for the square root of x. This is a simple enough one. Let's just go ahead and work it together. This is x to the 1/2 power. So I know that the domain for this is going to be closed 0 to infinity. Now when I look, I want to find the derivative, which I know is 1/2 the square root of x. When I think about where the first derivative is 0, I note that the numerator is never 0, so there are none coming from that particular possibility. The second is that the first derivative does not exist, but the function does. The first derivative does not exist at 0. Is 0 in the domain? As a matter of fact, it is. This gives us x equals 0 as a critical point. Let's see if it actually corresponds to an extrema. Well, it does not. If you think about the graph of the square root of x, it comes up like this. What's happening is at the origin, as it approaches from the right, we have a point of vertical tangency. For one instant, the slope of the tangent line goes vertical, which means it does not exist. Let's talk about locating these absolute extrema when they exist. The extreme value theorem says that if I have a continuous function over a closed and bounded interval, there must be an absolute maximum and minimum on the closed interval. Could be at A or at B endpoints of the interval. Otherwise, it must occur at an interior point of the interval, which would make it a local extrema as well. And that means, by Fermat's theorem, it must be a critical point. So in order to find the absolute extrema guaranteed by the absolute extrema theorem on a continuous function on a closed bounded interval, we're going to check the endpoints and the critical points of the interior of that interval. Here's the theorem that states it. Let f be a continuous function over a closed bounded interval I. This is required by the extreme value theorem. The absolute max of f over I and the absolute min of f over I are either at endpoints of the closed bounded interval or at critical points of f inside I. Our problem-solving strategy for locating them is pretty straightforward. We're going to evaluate the y value of the function at the two endpoints x equal a and x equal b. Then we'll find all the critical points of the function that are inside the open interval from a to b. And we'll evaluate the function, the y value, at those critical points. Then what do you think we do? Of course, we're going to compare the y values and pick the highest y value for the absolute maximum and the lowest y value for the absolute minimum. That's pretty much it in a nutshell. Remember that the absolute maximum is the y value. The x value is where it occurs. There can only be one maximum, absolute maximum, and one absolute minimum, though they can occur at more than one location. Let's now apply what we've learned to example 9, where we're tasked with finding the absolute maximum and absolute minimum of a polynomial function over the interval 1. We know it's an upward opening parabola, so we know already that it has no absolute maximum on the entire real number line, but we're not looking on the entire real number line. We're looking on the closed interval from 1 to 4. There must be an absolute maximum on that closed bounded interval because the function is continuous. So let's go ahead and check our 3 conditions to apply the theorem. It's continuous because it's a polynomial. Now, is it a closed bounded interval? 1 to 4 is closed because we include both the 1 and the 4, and bounded because they're not going to plus or minus infinity. So we apply our problem-solving steps and we evaluate f of 1 and f of 4. This gives me the value of, well, 0. Okay. And f of 4 gives me the value of 3. I'm not done because I have to locate critical points. When I look at the critical points, I'm going to be looking for the first derivative. I'm looking for where it either does not exist or is equal to 0. The first derivative is given by 2x minus 4. There's only one possible critical point coming from the first derivative equal to 0, which is going to be at x equal 2. It is a polynomial function, so we know that there are no possible critical points coming from it not existing. Now I need to evaluate the function at x equal 2 and add that to my list. This gives me 2 squared minus 4 times 2 plus 3. This is going to give me -1. When I look at these values, the next thing I want to do is I want to find the highest y value and the lowest y value between the endpoints and any critical points I found. The highest one is 3. So I have an absolute maximum of 3, which is occurring at x equal 4. Then I have an absolute minimum of -1, which occurs at x equal 2, the interior critical point. Let's look at the graph and confirm. You'll note in this particular one that I only graphed over the closed interval. We do have an absolute maximum up here, located when x equals 4. And the absolute maximum is the y value, which is 3. We have an absolute minimum of -1 occurring at the x value 2. The next problem is similar, but we're looking at the product of 2 trig functions. You will have to apply the product rule to find the derivative. We're looking at a closed bounded interval, 0 to 2 pi. We know that the function must be continuous because the product of 2 continuous functions is continuous. And we know that 0 to 2 pi is both closed and bounded. You can apply the theorem, so go ahead and locate your absolute max and absolute min, then turn the video back on to check. Let's look at example 10 together. Function is continuous, 0 to 2 pi is both closed and bounded. When we find the derivative, you can either leave it in cosine squared of x minus sine squared of x form, or convert it to cosine of 2x, which I chose to do. To find the critical points, I set the derivative equal to 0. Note that the derivative is always defined, so there are no critical points coming from that possibility. The next thing I do is the trig process of looking for solutions to the equation. Cosine of 2x equals 0 when 2x is some pi multiple of pi over 2. I got a common denominator, then divided both sides by 2 to get the expression pi plus 2 pi n, all divided by 4. Then I chose a range of values for n, both negative, positive, and 0, to find the ones that were in my interval 0 to 2 pi. This gave me pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. The next step is to evaluate the original function at the endpoints and the critical points. Evaluating the original function, sine times cosine, at both 0 and 2 pi leads to the value of 0. When we evaluate it at the critical points, we get that the value at pi over 4 and 5 pi over 4 is a positive 1/2. And at 3 pi over 4 and 7 pi over 4, it's a negative 1/2. Our absolute maximum is thus 1/2. And our absolute minimum is negative 1/2. They each occur in 2 places. Let's take a look now at this graph. Note that I've graphed it only over the region from 0 to 2 pi. You can see that we do have 2 absolute maximums and 2 absolute minimum locations, but 1 absolute maximum value of 1/2 and 1 absolute minimum value of negative 1/2. Let's take a look at the next example together, since it is a little bit more complicated with the exponential function. We want to find the absolute max and absolute minimum of x e to the negative x over 2 over the closed and bounded interval 0 to 5. We know exponentials are continuous functions, and x is a continuous function. So the product of 2 continuous functions is continuous. We also know that the interval 0 to 5 is both closed and bounded. Now we can apply the theorem. I'm going to have to evaluate at 0 and 5 and also critical points of the interior. To find the critical points, I take the derivative by applying the product rule and the chain rule. The derivative of x is 1 multiplied by the exponential, plus the derivative of the exponential invokes the chain rule. The derivative of the exponential is the exponential multiplied by the derivative of the power, which is a negative 1/2. And then it is multiplied by the first factor, x. I'll go ahead and factor out the exponential because, as we know, unless the exponential has been shifted up or down, it does not have any x-intercepts. This gives me in parentheses x1 minus 1/2 x. So the first derivative equal to 0, well, the exponential is never equal to 0 because e is a positive value, and raising it to a power will not make it 0. However, the second one does give me a solution or a critical value. This one is going to give me x equal 2. Is there a point where the function is defined, but the first derivative does not exist? And the answer to this is, well, no. There are none coming from this because the derivative, like the function, is defined everywhere, and in particular over 0 to 5. Now we're ready to go ahead and substitute in our values. We want to evaluate our function over the interval from 0 to 5, looking for the absolute maximum and absolute minimum. We substitute the two endpoint values first. This is going to give me f of 0, which is 0 times e to the 0th power. E to the 0th is 1, but 0 times that is still 0. The other endpoint is 5, which gives me 5 times e to the negative 5 halves. I'll have to approximate this so I can tell about how big it is. All right. The next thing that I'm going to do, this, of course, it can also be written as 5 divided by e to the 5 halves. Let me take my calculator, and you can take yours, and let's get an approximate value for that. I want to take 5 times the exponential raised to the negative 5 halves power. I got about 0.41. Now I need to evaluate at my critical point, x equal 2. When I substitute in x equal 2, I get 2 times e to the negative 1, which is 2 divided by e. When I take my calculator to compute that, I get the value of, oops, I forgot my negative 1. There we go, which gives me roughly 0.736. When I compare the three values that I got, the two endpoints and the critical value's y value, I can see that my absolute maximum is 2 over e, and it occurs when x equal 2. And my absolute minimum is 0. Let's take a look at the graph of this function. Notice that I only graphed it over the interval from 0 to 5. I kind of like this function, so I went ahead and graphed the whole thing just so you could kind of see what it looks like. We're only interested in the blue section, but notice how it does come up, has a high point, and comes back down to approach the x-axis. We have both an absolute minimum and an absolute maximum on the closed interval from 0 to 5. We have one example left, which is the function x times the natural log of x divided by 5. In order to apply this, we need to establish that the function is continuous and the interval is closed and bounded. The interval from 0.1 to 5 is closed and bounded. Is the function continuous? To decide that, we need to know what the domain of the natural log of x over 5 is. And to decide that, I need to take the x over 5 and say that this has to be greater than 0. That implies that x must be greater than 0. Because this does fall in that range, I know that this function is the product of two continuous functions is continuous. That's condition 1. The second two conditions are met by the closed bounded interval 0.1 to 5. You will need to use both the chain rule and the product rule in order to find the critical points for this function. Go ahead and pause the video, work it out, then turn it back on, and we'll compare our answers. Let's compare and see what you got. When I take the derivative, remember that the derivative of the product rule is going to give me 1 times the natural log plus x times the derivative of natural log, 1 over the argument times the derivative of the argument. When I simplify, I get the natural log of x over 5 plus 1. I look for the critical values by setting the first derivative equal to 0. This will lead to the following equation. I move the 1 to the opposite side to have the natural log equal to -1. Then I switch to exponential form, where e to the -1 is equal to x divided by 5. I rewrite the exponential by putting it in the denominator and cross multiply. Then I solve for x to get 5 divided by e. Notice that there are no places that are in the domain where the first derivative is not defined. Now I need to evaluate the original function at the endpoints and at the critical point. This is a little bit tricky in some of these, especially on the critical point where I have the natural log of 5 divided by e, all divided by 5. 5's cancel, and it gives me 1 divided by the exponential, and that makes it e to the -1. The natural log of e to a power is the power, which gives me -5 over e. This turns out to be the absolute minimum value, which is occurring at 5 over e. Our absolute maximum value ends up at the right endpoint of the interval 5. And the maximum value is 0. I forgot we have one more problem to work, but you'll be happy to know that this is pretty much a straightforward one. The difficulty on this one is that our interval is neither closed nor bounded. The interval goes from -infinity to infinity. We can consider it to be closed because infinity and -infinity are both open and closed, but it's definitely not bounded. We're not guaranteed, but let's go ahead and see if we can find them anyway. Start by finding the critical points and then evaluating the function at the critical points. And we'll look at the graph and talk about what we have. Again, we want to be careful in this problem that we do not assume that we can use the theorem. Because it is not a bounded interval, we can't. We can still look for them by finding the critical values, but we cannot assume that they are absolute extrema without looking at the graph. We find the critical points by finding the derivative and setting it equal to 0. The derivative is a polynomial, so it's always defined. Notice that in the next step, I divided by 12, but not by x. You must not divide by the variable or you will lose a critical point. X in the original problem is allowed to be 0. When you divide by x, you're saying x can't be 0, but that's not true. It can. Make sure not to divide by the variable. Instead, what you want to do is you want to factor it out as a common factor. Then you will have 3 different critical values: 0, -3, and 1. Substitute these values into the original function to come up with 3 possible values. It appears that 0 is a maximum. As we'll see, it may not be. It appears that -135 is a minimum. Let's take a look at the graph and see what they actually correspond to. This is the graph of a fourth degree polynomial with a positive leading coefficient, so it opens up on both sides. There is no absolute maximum. In this case, it turns out that the zero is a local maximum. It also turns out, if we scroll up, that we do have a local minimum here at, what is that? 1. And we probably have another one at -3 if we could only find it. But I'm scrolling and scrolling and, well, it's not showing up. But it's got to be up. There it is. That actually turns out to be an absolute minimum because there is no y value lower than that. You cannot assume that they're absolutes when the conditions are not met. Make sure that you check the conditions before applying the theorem. In the next video, we'll be talking about the mean value theorem, which is in some ways a most valuable theorem. Yes, pun intended. When we think about the mean value theorem, it's going to let us make some assumptions about the shape of the graph and also allow us to prove some very important theorems now and at the end of the semester when we study integration. After the mean value theorem gives us these important theorems for now, we'll be able to take a closer look at the shape of graphs using all the techniques we've developed in algebra and calculus. See you for the next video.